Yeah, we move on with SymPy again as we consider simplification and manipulation of expressions with SymPy. Okay, some of them are going to be repetitions of some of the things we've done before, but it's important to uh, establish those things with all clarity. So, simplification and manipulation of expressions with SymPy. SymPy is a Python library for symbolic mathematics, as you already know. SymPy means symbolic Python. So, unlike numerical computation libraries, SymPy works with exact symbolic expressions. Using SymPy, we can simplify algebraic expressions, expand and factor polynomials, manipulate trigonometric identities, work with logarithms, perform symbolic substitutions, rewrite expressions, evaluate expressions numerically. This lesson focuses on symbolic simplification and expression manipulation. So, of course, in the first two videos, I already talked about how to install SymPy. We do that like we install every other library in Python. Just use pip space install space SymPy. Okay, and after doing that, each time you need to use it, you need to uh, import it. So to import, you have import SymPy as SP or as NSM or as SY, whatever you want to import it as. Okay. So then the next thing is you want to create symbols. So each time you need to do a task using SymPy, one of the first things you do after installing or after importing is to create symbols. So symbolic variables are created using symbols. So it is a generalized form. Although if you want to import a single symbol, you can use symbol with capital S that without plural. But symbols is more like a generalization of every other thing. So symbolic variables are created using symbols. Example, X, Y, and Z are symbolic variables. So to do that, so first of all, if you want to create one symbol, like I said the other time, you can say X SP dot SP is SymPy now, capital S, but no S at the end. So you can create using that. That's creating this is for single symbol now. Single symbol. Single symbol. But if you want to create multiple symbol, then you have multiple symbols rather. You then have x, comma, y, comma, z equals sp dot symbols, x space y space z. And then if you create an expression with that, that's x plus y plus z. And then you can print all that to be x plus y plus z. So building symbolic expressions now. So expressions behave like algebraic formulas. So example, you have x plus 2 raised to power 2. So x is sp dot symbols x because that's the only variable you have there. Then the expression is x plus 2, star, star 2. Star, one star is multiplication, two stars is power. Then if you print the expression, you have x plus 2 raised to power 2 like that. So here we're talking about simplification and manipulation as you're going to see later. So if you want to see more expressions, you can have something like expression 1, which is x raised to power 2 plus 3x plus 2. Expression 2 is sine x plus cos x. But because you cannot get sine and cos on their own, you have to bring it from SymPy to. So that's why you have sp dot sine x plus sp dot cos x. Then expression 3, you have sp dot exponent x. So if you print all of them, you have x squared plus 3x plus 2, sine x plus cos x, and exponent x like that. Then you can expand expressions. Expansion multiplies products and powers. So if you, for example, x plus 3 raised to power 2 becomes x squared plus 6x plus 9. We know that normally, but SymPy can do that for you. So you have x equals sp dot symbols x, then expression x plus 3 raised to power 2. So in expanded form, you have sp dot expand of the expression. And then when you do that, SymPy does it for you. You have x squared plus 6x plus 9, just like what you have over here. Then expanding multiple factors. So you can expand multiple factors also with SymPy. So imagine the expression x plus 1 times x minus 2 times x plus 4. So if you expand that, you have sp dot expand the expression, and then you print the expanded expression, which is x cubed plus 3x squared minus 6x minus 8. So to do this, it's going to be take a bit of time. But to set the code up, just declare the expression, expand, and print, and you have x cubed plus 3x squared minus 8. What if I make it like x squared in here, x squared here, plus x minus 1, that's also possible. So we now have something of order 5 now instead of or there are four instead of three. So we can have that's possible. So it just does it in a blow. So expanding trigonometric expressions. Now, SymPy can expand trigonometric identities. Example, if you have sine x plus y, I have a playlist on trig where we talk about these things. So if you have sine x plus y normally, that's simply the same thing as sine x. That's like sine x cos y plus uh, cos x sine y, something like that. That's what that looks like normally. So SymPy can do the same thing. So you have you set up the symbols x, y, sp dot symbols x space y. Expression is sp dot sine x plus y. Expanded, and you have sp dot expand underscore trig expression. So print, you have expanded. So in this case now it is expand underscore trig. That's the keyword here. Very important. Expand underscore trig. So now you see it gives you sine x cos y plus cos x sine y, or if you like, sine x cos y plus sine y cos y, just like what I have over here. So that's sine x cos y plus cos x sine y. So then you can also factor expressions, right? Using SymPy, factoring expressions. So if you factoring reverses expansion, so if you have x squared plus 5x plus 6, it becomes x plus 2 into x plus 3. So if you factor this, you have x equals sp dot symbols x, expression x squared plus 5x plus 6. So to factor that, you have sp dot factor expression. Then if you print that, you have x plus 2 into x plus 3. So, and then factoring higher degree polynomials, you have x cubed minus x squared minus x plus 1. So, sp dot factor, you get x minus 1 squared into x plus 1 for that. So, have that like that. Then you can simplify expressions. I mean, we've seen this in almost, I think in all the three videos so far on SymPy. So the simplify function applies many simplification techniques automatically. So example, x squared minus 1 over x minus 1. That's a common example we've been doing. I think I want to change it this time around to say, let's switch it up to x squared minus 4 all over x minus 2 so that we have for a change, right? Okay, this is still x squared. Now minus 4 and x minus 2. So the answer can now be x plus 2. So if you run this now, this becomes x plus 2 like that. Now we can combine fractions. Okay, I mean, this is a new one. I've not done this, talked about this in any of the previous videos. So the together function combines rational expressions. So example, you have 1 over x plus 1 over y. So to deal with 1 over x plus 1 over y, I mean, that's an elementary thing. So you have 1 over x plus 1 over y. So you take the LCM of x and y, which is xy. X goes in x, y times. So y times 1 is y. Plus y goes in xy, x times 1 is x. So finally, you have x plus y all over x times y. And that goes like that. So we have that. So x plus y over x, y. So you can do that using SymPy to sp dot symbols, create symbols x, y. Then the expressions, you have 1 over x plus 1 over y. Then combined, that's the sp dots together. Together is the keyword of the expression, and then you reprint combine and you get x plus y over x, y. Then you can also split things into partial fractions. So the apart function separates rational expressions into partial fractions. So you have express equals, okay, imagine the same x plus y over xy that we got from 1 over x plus 1 over y. We can separate it. So you separated, you have sp dot apart. So that's talking about partial fraction. So apart expression, comma x. So you print separated, you have 1 over y plus 1 over x. So we go back to where we are coming from. So it separates rational expressions into partial fractions. And that's the job it's doing right there. So it separates into partial fractions like that. And then we move on to okay, I didn't run this. Yeah, that's it. So collecting like terms, we saw collecting like terms in the last video. So the collect function groups coefficients by powers of variables. So x is sp dot symbols, x create a symbol x expression 3x squared plus 2x minus 5x squared plus x minus 7. So here 3x squared and 5x squared definitely look alike. So 3x squared minus 5x squared minus 2x squared. 2x plus x is 3x, then you have 7. So but to do that, you set up the symbol, you write the expression, you collect it. So sp dot collect the expression with respect to x. Then you print collected and you have your results. like that. Then collecting, you can also collect by expressions too, right? So imagine you have x sine x plus sine x. Of course, you see the reason for this SP is because sine x cannot occur of its own accord. So if I remove this SP now, you see there's going to be an error. There automatically be an error. So it tells us name sign is not defined because sign can only come from SymPy or maths or something like that. But here, SymPy is what we're dealing with. So basically you're saying x sine x plus sine x. So, and that's why if you do that, you get x plus 1 into sine x. So that's when you collect. So see why that is the case here. So you have x sine x plus sine x. Definitely, sine x is common. So you have sine x into x plus 1. So it's more like you have sine x is common, first of all, right? And you have x sine x divided by sine x, you know, this sine x we brought out here, plus sine x divided by sine x again, so that you then have sine x. So you have sine x into sine x cancel, so you have x plus 1. So then this is equal to x plus 1 sine x. And that's exactly what that gives us right up there. So you have x plus 1 multiplied by sine x. Then you can simplify powers too. So use the power simp keyword. The power simp function combines powers. So example, you have x raised to power 2 times x raised to power 3 equals x raised to power 5. So create your symbols, and here you're guaranteeing that x is positive here, because if x is not positive, you're going to have an issue with something like x raised to power 3 and x raised to power 5. So the expression is x squared plus x raised to power 3. So combined, you have sp dot pow simp, simplifying powers of the expression. So you have x raised to power 2, x raised to power 3 being x raised to power 5, like that. Then expanding powers, you can expand powers too. So if you have x comma y, sp dot symbols x comma y. So expression x times y raised to power 3. So that means x raised to power 3 times y raised to power 3. So expanded, you have sp dot expand power base, expand power base of the expression. So you have this now. So this power is applying to both. So you have x raised to power 3 times y raised to power 3, and that's exactly what you have there. So imagine if you have here that you have, first of all, have x raised to power 2 multiplied by y all raised to power 3 now. So it's going to be x raised to power 6, y raised to power 3, like you have now. They can have logarithmic manipulation. SymPy can expand and combine logarithms. So you have log xy from the law of logarithm, of course. I have a playlist on logarithms and indices and logarithms. So you want to check that out if you're interested in knowing more about logarithms. So log xy equals log x plus log y. So expanding logarithms, now you have x comma y, sp symbols xy. Guarantee that it is true because logs only work for positive numbers. If not, that's why you have to guarantee that each of them is true. So the expression you have log x, y. So expanded now you have sp dot expand underscore log expression. So just, the other time we have expand underscore trig for trig. So for log now. So if you print that, you have log xy is basically the same thing as log x plus log y. Of course, don't forget that you can only get log from SymPy. That's why you need sp dot log x times y, like that. And then we move on to combining logarithms. So just like you can expand logarithm, you can combine it. So for this same result now, so if the expression is sp dot log x plus sp dot log y, of course, log x plus log y to the same base is going to be log xy to that base. So here now you have the combined, now be sp dot log combined expression. So if you print the combined expression, you then get log x times y, like that. Then we can have trigonometric substitute simplification. So SymPy can simplify trigonometric identities. So example, you have sine squared x plus cos squared x equals 1. So trigonometric simplification, so you have x is sp dot symbols x. So the expression is now sp dot sine squared x plus sp dot cos squared x. So simplified, you have sp dot trig sim of the expression, and if you simplify that, you get 1 right here. I think we've seen this in every video since I started talking about uh, SymPy. So expanding trigonometric functions now. So if you want to expand sine 2x, of course, some sine 2x is like this. If you It's just as a way of refreshing our minds about that. We know that if you have sine 2x, sine 2x is simply the same thing as sine x plus x. And just like we have the other time when you dealt with sine x plus y, that's sine x cos y plus cos x sine y. So in this case, we do the same. So that's sine x cos x plus cos x sine x. So it turns out that since x and x are the same, it turns out that sine x cos x is the same thing as cos x sine x. So we can just write them the same way. So that now you see this and this are the same. So it's more like you have two of them. So you have 2 sine x cos x right here. So and that's why SymPy can have that sorted for us. So to expand that, now you have expression is sp dot sine 2x. So expanded, you have sp dot expanded, that's called trig expression. So print expanded, you have 2 sine x cos x like that. Then for substitution, the substitution function replaces symbols with values or expressions. So single substitution, now so you have x comma y is sp dot symbols xy. The expression is x squared plus y. So results express, so the expression now substitute x 3 for x. So in this case, now since you are substituting for only x, we get 3 squared plus y, which is y plus 9. So, but it's also possible to do double substitution. We substitute for x and y, just like we have in the next expression. So you have x squared plus y. So you are substituting 2 for x and 5 for y. That'll be 2 squared plus 5, which is 9 again, which is 9 here. So you can do one substitution or two. So here you didn't substitute for y, so y it remains symbolically. Then substituting expressions now. So you have expression x squared plus 1 equals x, expression is x squared plus 1. So the results, you don't want to substitute. Anywhere you see x, you put y plus 1. So instead of x squared, now you have y plus 1 squared plus 1. And this is what exactly you have right there. Then you can talk about numerical evaluation. So the eval function converts symbolic expressions into decimal approximations. For instance, you're dealing with this expression pi plus square root of 2. Of course, pi comes from SymPy, square root comes from SymPy too. So normally, if you are doing it symbolically, just have pi plus root 2. But here now you want to evaluate. So if you do that, you get this. And don't forget, you can have higher precisions. Okay, this is what exactly we even have here. So if you print, you want 50 decimal places, you can have that too. So it's more like you just want to, you can also, pi is one thing that is really interesting. It is an irrational number. So you can have something like, say, sp dot pi. Okay, dot eval. Okay, like it's like this thing is here listening to me. Okay, so we now you want it in maybe 200 decimal places. I know there are challenges about people reciting the value of pi up to 32 decimal places and things like that. So that is 3.1415926535897932384626433832795 like that. Okay, so that is numerical evaluation using the eval function. And beautifully, you can specify how many decimal places you want. So if you want just one decimal place, okay, you have 3.1. If you want one, you put 2. If you want 11, you put 12. So to 12 decimal places, this is what you have: 14159265 359. 14159265. So we have all of that going. So you can rewrite expressions too. So the rewrite function converts expressions into equivalent forms. So you're writing with exponentials, for instance, x is sp dot symbols x, you create your symbol, expression is sp dot sine x. So you now want to rewrite that in exponential form. So rewrite sp dot exponential. So and that's minus I into e raised power ix minus e raised power minus ix all over 2. That's how to you can write an x in that form. So then we have rational simplification. So the cancel function removes common factors from rational expressions. So, for rational expressions, now imagine you have x squared plus 2x. Of course, you have created your symbol, x squared plus 2x plus 1, which is x plus 1, x plus 1, all over x plus 1. So x plus 1 cancels out. So simplified, now you have sp dot cancel expression. So you then have x plus 1 like that. So that cancels things out. Then imagine you can also have numerator and denominator. So here now you have expression x plus 1 over x minus 2. So the numerator, denominator, you can have sp dot fraction expression. So you print the numerator, you print the denominator, and because you have x plus 1, x minus 2. So what if you have x squared, you know, plus x minus 7, okay? All over that. So just extracts. Okay, yeah, I think I did wrong with that because a square should be star star. Okay, so you have x squared plus x minus 7, and the denominator is x minus 2. Then we can have polynomial manipulation. So SymPy provides a poly class for polynomial operations. So creating polynomial objects, first of all, x is sp dot symbols of x. So the polynomial is now sp dot poly, capital P, don't mind you. So that's x cubed plus 2x squared minus x plus 7 with respect to x. So x is the variable we are focusing on because a polynomial can have more variables. So the print poly now gives you x cubed plus 2x squared minus x plus z, x, and the domain is this. I think the domain is infinity. Maybe zz has been written as infinity or something, I'm not sure. Then you have polynomial degree. You want to know the degree of that polynomial, so you click on this. Okay, because I didn't run this now, this is not working, so now it works fine. So the degree is 3. And then if you extract the coefficient, that's for x cubed, the coefficient is 1, x squared, the coefficient is 2, x, the coefficient is minus 1, and the constant is 7. So then you have, you could talk about, what is it now? Okay, I mean, if you change it, what if you now have this one to be minus 5x? So it automatically changes. Okay, it should be minus 5 times x. I keep making that mistake. So don't forget multiplication is star, power is power, star star. So it is 3 degree, it's still degree 3, but now the coefficients are changing because now this is going to be minus 5 instead of minus 1 like it was. So verifying algebraic identity. So you can verify if two expressions are the same, right? Expressions can be verified symbolically. If the difference between two expressions simplifies to 0, then the identity is true. So if you have created your symbol with x, the left is x plus 1 squared, and the right is x squared plus 2x plus 1, which we know are the same basically. But to verify that they are the same, you can just say sp dot simplify left minus right. So if the results you get, so if you print your verification, if the verification is 0, then it means that the expressions are the same. The expressions are the same. Then combining multiple techniques now. Complex expressions may require multiple simplification methods together. Okay, complex expressions may require multiple simplification methods together. So in this case now, imagine you've created your symbol x, and then you have x squared minus 1 over x minus 1 plus sine x squared plus cos squared x. Sine squared x plus cos squared x. Of course, this is 1. And then when you simplify, this is x plus 1. X plus 1 plus 1, that's x plus 2. That's exactly what is happening here. So what is happening there is you have x squared minus 1. So it's like you have x squared minus 1 all over x minus 1 plus sine squared x plus cos squared x. So of course, we know this is x minus 1 into x plus 1 all over x minus 1 plus sine squared x plus cos squared x. So if you simplify that, right, x minus 1 cancels this. So we have x plus 1, sine squared x plus cos squared 1, cos squared x is 1. So everything together is x plus 2. And that's exactly what happens here. So when it's all simplified, we get x plus 2. Then best practices now. What's the best thing you do with all this? So first of all, use specific simplification functions. Prefer factor, expand, trig, simp. If you want to simplify trig, you can cancel if you want to remove some factors instead of always using simplify. So you can use specific simplification functions instead of just simplifying all the time. So you only use simplify when it's absolutely necessary. Then you have another thing is use symbol assumptions. Example, x greater than 0 can improve simplification results. So guarantee that x is always positive if it is always positive, so that you eliminate the extra work of thinking of x being negative. Very important. So use symbol assumptions. Then keep expressions symbolic. Prefer exact symbolic values such as 1 over 3 instead of decimal approximations. So decimal approximations like 0.3333 is not as good as when you have 1 over 3, which preserves the form of the expressions. So symbol assumptions now. So you imagine x is sp dot symbols, declare x. So starting from where you declared, you create the symbol, you always say positive is true. That is, the x value is always true. So whatever happens, so the system can operate knowing that x is always positive without worrying about whatever the. So normally square root of x squared should be plus or minus x. But since you have guaranteed that the x is always positive, so it is so you eliminate the possibility of thinking about the about x being negative. So the expression here is square root of x squared. So if you print that expression, simplify the expression, you get x straight because you have guaranteed that it is positive. So, but if you do not put this now, it will probably not give you that. So it will keep it as x squared, root x squared plus or minus root x squared. So it's better to guarantee that it is positive if you are sure that is the case though. So you don't just say it is positive because, but because it is really positive. So that helps some simplification. Then common errors using Python math functions instead of SymPy functions. So it is incorrect to say math.sin x. The correct thing is sp.sin x because you are doing symbolic stuff. So if you use sin x, it won't get this. You may not get the same result as when you use sp.sin x because you are dealing with symbolic Python, symbolic mathematics. So forgetting symbol definitions too can be a problem. Symbols must be defined before you. So if you don't create the symbols X, Y, maybe you created symbol X, Y, Z, and you now get somewhere you want to use W, it's going to throw up an error. So if you want to use W, you have to also create it as one of the symbols. Okay. So, and then don't forget keywords like sine, exponent, trig, all those things. They come from SymPy, so they don't stand on their own. So you have to use SP dots, and then even the keywords to come from that. So we have a mini project here, symbolic algebra calculator. So import SymPy as SP, then create symbol X. Expression, we now have this expression x plus 1 raised to power 3. So we want to do different things with it. Number one, we want to print the original expression. Okay, let me just run it first, and you can see all the results here. So print original expression, that's why you have x plus 1 raised to power 3 here. Then expand it, if you expand as x cubed plus 3x squared plus 3x plus 1. Then factor it. This is the next one now. So sp dot expand is for expansion of the expression. Factor, if you factor it's x plus 1 cube. Then what else? Differentiate it. If you differentiate that, that's into 3 into x plus 1 squared. That's exactly what we have. Then evaluate the value of the expression, substitute x into it. So that x equals 2. So 2 plus 1 is 3. 3 raised by 3 is 27, like that. So you can also, what if I make it a bit more complicated and say this is x raised by 2 plus x plus 1 and do the same thing. So it gets more serious, and you see that x squared plus x plus 1 raised to power 3. So if you expand, you get x raised to power 6 plus 3x raised to power 5 plus 6x raised to power 4 plus 7x raised to power 3 plus 6x raised to power 2 plus 3x plus 1. Factored, you have x squared plus x plus 1 all raised to power 3. Derivative, of course, different. That's 3 into differentiate inside, that's 2x plus 1, then x squared plus x plus 1 raised to power 2. And then if you simplify, you get 6x plus 3. So you can see 3 can be factored. So you have 3 into 2x plus 1 into x squared plus x plus 1 raised to power 2. Then if you find the value of the expression at x equals 2, that's 2 squared. 2 squared is 4. 4 plus 2, 6. 6 plus 1, 7. 7 raised to power 3 is 343. So you can do this kind of thing like that. So if you have a particular expression and you want to do different things on it, you can actually set it up like this, and it becomes like a mini solver, a mini calculator for symbolic algebra. So in conclusion, in this lesson, you learned how to create symbolic variables, build symbolic expressions, expand and factor expressions, simplify algebraic formulas, manipulate trigonometric identities, work with logarithms, perform substitutions, rewrite symbolic expressions, evaluate expressions numerically, manipulate rational and polynomial expressions. Then SymPy is a powerful symbolic mathematics system for algebra, calculus, and engineering, physics, and scientific computing, like that. So we have some problems here for you to deal with. So, first, you want to expand x plus 4 raised to power 2. You want to expand x minus 2 into x plus 5. You want to expand x plus 1 into x plus 2 into x plus 3. So just follow the previous examples. Just create the symbol, create the expression, and then expand as necessary. That's sp dot expand of the expression. Then problems 4 to 7, if we can. Okay, let me take 4 to 6. So 4 to 6 now. You want to factor x squared minus 4 because that's x into x squared minus 4 is x minus 4 into x plus 4. Then you want to factor this x plus 3 into x plus 4. Then you want to also factor this x cubed minus x squared minus x plus 1. Then problem 7 and so 7. Okay, let me take 7 and 8 here. So simplify x squared minus 1 over x minus 3. That's x minus 3 into x plus 3. So x minus 3 cancels, so you have x plus 3 left. You want to simplify this. Of course, x plus 1 is the result, as you can already imagine. So we did exactly this. Maybe I should make it something else. Yeah, maybe I should add 1 over z to it. Okay, I think it's gone far. Where is that now? Yeah, so maybe I should add 1 over z to it. So 1 over z, at least for a change. Okay, so we have that, then that's problem 9. Combine the fractions 1 over x plus 1 over y plus 1 over z. Then problem 10, perform partial fraction decomposition for x plus 2 over x into x plus 1. So it can do that neatly. We already have a mathematical way of doing this. So SymPy will do it straight forward. So collect like terms now. So 3x squared, 2x squared, that's x squared plus 12x minus 1 easily. Then problem 12 and 13. Collect terms involving sin x sin x plus 2 sin x. Sin x is common, so you have sin x into x plus 2. So that's like x plus 2 multiplied by sin x. Then problem 13, simplify sin squared x plus cos squared x. That's simply 1. Then problem 14 and 15. Expand the trigonometry identity and 2x. Of course, that's 2 sin x cos x. Problem 15, expand the logarithm log xy. Of course, that's log x plus log y. We've done that a lot. Then combine the logarithm log x plus log y. So we've done all of that too. So you can just change the maybe instead of xy, you can have maybe pq just for a change. Then we write using exponential sign x. That will rewrite it in exponential form uh with even some negative complex values. Then problem 18, substitute x equals 3 into x squared plus 4x plus 1. And then substitute x equals y plus 1 into x squared plus 1. So, this will just be 3 squared plus 4 times 3 plus 1. That's 9 plus 12 plus 1. That's 22 altogether. And substitute y plus 1 for x into this. So that'll be y plus 1 squared plus 1, which we did before. Then problem 20. Okay, we did exactly the same thing. So it's more like repetition of some of those. So you can just switch things up and see how they go. So with this, we come to the end of this interesting video on simplification and manipulation of expressions in SymPy, using SymPy with SymPy if you like. So thank you so much for listening. Let me know how helpful this is for you. And there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and subscribe right now, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, don't forget to click on join to become a member of this channel, and that comes with some special privileges that you find out when you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.